Okay, so welcome back. The class is shrunk to enormously small size from being very large. I think the lab assignment being due is probably keeping people away. So all of you get bonus points. No, I'm just joking. Okay, so we will just resume our normal lecture schedule. Last week was all guest lectures. Hopefully you got something out of the guest lectures. Send me feedback if you have any comments about the whole concept of a guest lecture. So what I'll do is just wrap up the discussion on XFS that was remaining from 2 weeks ago. We'll finish that. I'll talk about distributed middleware for the rest of the class. Next time we'll talk about distributed data processing systems, and then last class next Monday on security. Okay, then we'll be done with the course. All right. Okay. So just to remind everyone where we were, because it's been almost 2 weeks now, we were talking about this system called XFS, which combines two concepts. One is it combines RAID, which is a redundant array of inexpensive disks. Specifically, XFS uses this concept of network striping and RAID over a network, where you take a file, you partition it into blocks. Each block goes to a different server. So that means you're striping over a network. And then you are essentially also taking those blocks and making it a software RAID 5, which means you'll take the blocks, compute a parity. That parity block will go on yet another machine. Okay? So this is called network striping. That's the first thing that XFS does. Now XFS by no means actually came up with this notion of network striping. There are other file systems that actually did that before XFS. Okay. The other important concept in XFS is this notion of using a log structured file system, okay, where you are essentially writing out data sequentially in the form of a log. Okay. And I was talking about the motivation for doing this just before the class ended 2 weeks ago. Okay. The main issue in log structured file system, which is essentially a separate file system from XFS, but XFS borrowed that concept and embedded it into the file system. Okay. So if you search for log structured file system, you'll see the original paper on LFS. It's a very nice idea. Okay. It is motivated by the use of large caches by the operating systems, large memory caches. Okay. Every file system that you have will essentially have a cache in memory. Whenever you try to read some data, first the OS will check if that data is already, that file or that file block is already in the cache. If so, you'll return it from the cache. Otherwise, you'll go to the disk and read it. Okay. So now the thing is, if you have a large enough cache and you have well-behaved applications, a lot of your read requests are going to become cache hits, because you might actually have locality of access, which means the cache will actually pay off in terms of the data that you are accessing will be in the cache with reasonable probability. Okay. There will be, of course, some number of cache misses, which you still have to get from disk. But once you get that data from disk, you cache it, then subsequent accesses to that file or those blocks are serviced from the cache. But writes, on the other hand, still go to the disk. Okay. So if you think about this bigger disk, if you have 50% of the requests being reads and 50% writes, and they all go to the cache, okay, what will trickle down is all the writes have to be sent to the disk, because you have to make the data persistent. But most of the reads are absorbed from the cache. Okay, so there will be only a few read requests trickling down, but most of the write requests trickle to the disk. Okay. So if you look at the disk traffic, even though the file system traffic is maybe equally balanced between reads and writes, the disk traffic looks predominantly write only. Okay, so what the disk is seeing are mostly write requests, because the read requests are getting served from the cache. Okay, that's normal in many file systems whenever you have a large cache. If this cache was missing, all the reads and writes would go to the disk. You would see an equal number of reads and writes, okay, in this particular example. Is this clear what I just said? Okay, so now the question is, if you have a file system that is seeing mostly write traffic, how would you optimize its performance? Okay. Now to understand this, you have to understand how disks work. Okay, most of the not solid state disks that you have today, these are more traditional hard drives that you had that were common until a few years ago. Okay. So if you think about a disk, if you've seen what a CD looks like, okay, a disk essentially has CD-like platters. Okay, so there are some number of platters that are all spinning. Okay. and then there's a disk head that is essentially going to read or write data which are recorded in concentric circles. Okay? So whenever you try to read a block, first you have to move that disk head to the right track on that disk. That's called seek. So you're going to make the head move and it positions itself on the right track. Once it's on the right track, then you wait for the data you are trying to read. Let's say that's that block there. You want to wait until it spins under the disk head, at which point you will read and write. Okay? That's how normal magnetic disks work. Okay? So this is basically what you may have learned in an undergrad operating systems class. Okay. Now the question is, if that is basically the behavior of a disk, and if your traffic was predominantly write only, how could you optimize the performance of the file system by optimizing the performance of the disk? Okay. And the basic insight is you want to reduce the time spent in doing a seek and waiting for the right block to spin by. Okay, because that's just wasted time. You can't do any I/O while your disk head is just moving back and forth to go to the right block. Okay. That's just wasted time. Okay, only when you're actually reading or writing is the disk doing any useful work. Okay? So every read request would normally incur, or a write request for that matter, would incur a seek, and then there will be some rotational latency overhead. So if you eliminated a seek and rotational latency overhead, you are going to spend more time doing reading or writing. Is that clear? Okay. So then you are going to have higher throughput because you are spending less time doing seeks and rotational latency. So then the question is, what would you do if you are told that most of the I/O requests are writes and you want to improve performance? How would you try to lay out your blocks or write the blocks to disk? Okay. Normally we assume random access, which means any block can be stored anywhere on disk, which means after you written one block or read one block, the next block would be at an arbitrary location where you will have to perform a seek and go there to read or write it. Okay. So can we eliminate that overhead somehow? Sorry?
Use sequential.
Okay, use a sequential form of writing. Okay. That's what a log is. A log is essentially a sequential write that you're doing. Okay. So basically what you're going to do, the best thing you can do is every block, if it's a write request, you store one block at a certain location. Okay, the next block, if it's adjacent to that block, there is no seek involved. You just write it to the next location, and the next location, and the next location, and so on. Okay, which completely eliminates the seek overhead. If you had stored one block on track I, another block on track J, another block on track K, you would be seeking back and forth, and that will reduce your throughput. But if you write it out sequentially, you are eliminating throughput, eliminating seeks altogether. Okay. So the whole idea of a log structured file system is that you try to write all the blocks sequentially one after another, and that is why it's called a log. You're just writing it in a log fashion. Okay. The only reason you can do this is there are few read requests that cause seeking to begin with, so you can just keep writing. Occasionally there will be a seek that will allow you to, require you to go to some other location to read that block, but then you can come back and start rewriting the log again. Okay. So the whole purpose of log structured file system was essentially buffer writes in memory and write them in contiguous chunks or contiguous set of blocks into what are called segments in a log like fashion, okay, which will dramatically improve your performance. Okay. Now the important part in a log is if you open a file, you modify it and save it. Okay. Normally your file system would go back. Let's say the file is stored at this location that I marked here. If you open that file and modify it and save it back, normally the file system would go and overwrite those contents there. Okay. In a log structured file system, since you're writing sequentially, you cannot actually do this. So if you modify a file, you are going to write it where the new log ends, to the end of the log. That's the whole idea of a log. Okay. And then you are basically going to mark this block as being deleted. Okay. If you modify the file again, you will write it at the end of the current log, and then whatever block has been stored previously will be marked as deleted. Okay. So occasionally you will have to do a garbage collection because your log where there are holes in your log. So you want to defragment it and reclaim that space. Okay. So all log structured file system, unlike any traditional file system, also have to run a garbage collection process because overwriting is not allowed, because logs will mean you always write to the end of the log. If you have modified some data that already exists somewhere else, you write the new version of that data at the end of your log, and that data gets deleted. Is that clear? So if you think of this as a sequential log rather than a disk, you are essentially writing to the end of the log. So if you modify a file that was stored here, you are going to write the new version of the file at the end, and this will be marked as deleted. If you modify the file and save it again, and the log is moved here, you are going to write the new version here, this is going to be deleted. So all of these are holes that you have to reclaim through a garbage collection process. Okay? So that's a disadvantage of a log structured file system, which means you have to run garbage collection, but the writes are very efficient. Okay? So, and that's what it says, must clean holes written by write. So the two concepts in XFS is you do a software read, and then you also write out all files as a log in a log structured fashion. And by combining these two, you essentially get fault tolerance because you are using RAID. You get parallelism because you are using multiple nodes. You are sending your file and spreading it across multiple machines. You get the benefits of log structured organization, which gives you high performance. Okay? Now, one thing you have to keep in mind is now that all machines are slowly switching to solid state disks or SSDs, okay, this optimization no longer gives you any benefit, because in a solid state disk there are no moving parts, there is no seek. Okay, because there's nothing spinning like a CD. It just basically looks like a memory where you can go and read or write any location with very low latency. Okay? So log structured organization only makes sense when you have traditional hard disks, okay, not when you have solid state disks. But when XFS came out, which was almost 20 years ago now, there were no solid state disks, so this made a lot of sense, okay? But not necessarily today. RAID and all of those other concepts still make sense today, okay, but not necessarily LFS for the original reasons it was developed. Okay? So SSD is also used in many cases log structured like system, but for other reasons, not for this reason. So that's XFS combined with software RAID, which is actually shown here. So you essentially have a log. Okay, now what you're going to do is logs are being written sequentially. You chop it up into blocks. Each block becomes a parity group. You compute the parity. You take those 4 blocks. There are 3 data blocks, 1 parity blocks. You then put it on 4 different servers. Each of these disks is a server on a different machine. Okay, so you put block 1 of that log on machine 1, block 2 machine 2, block 3 machine 3, parity group machine 4, and repeat, okay, in a RAID 5 fashion. Okay, so this is how those two techniques are combined in XFS. Is this clear? Any questions here? Okay. So I have 2 more file systems to talk about very quickly, then we'll move on to middleware. Okay, so next file system is the Hadoop file system, or HDFS. Okay. Next class we are actually going to talk about MapReduce and Hadoop and so on. So if you don't know what that means at this moment, it doesn't matter. We're only going to look at the file system part of Hadoop. Okay. So it's a distributed file system, which means data is stored across multiple machines. It is designed for high throughput, very large data set. Okay. As we'll see next time, Hadoop is used for data processing. So there's a lot of data that you want to process in some shape or form. So you first store that data in the Hadoop file system, and then you have machines that read it and do processing of that data. Okay. So this is designed as a file system to store very large amounts of data. Okay. So data sets that could be gigabytes or terabytes in size, not data files that are kilobytes or megabytes in size. So it's looking at storing very large files is the way you want to think about it. Okay. So you want to optimize the file system for batch processing, okay, which means that you will read the data, process it, store intermediate results, rather than interactive processing. Nobody will use HDFS to read a file, edit it, and save it back. That's more interactive. That's how users use data in a traditional file system. This one is designed for batch processing, designed for large data sets. Okay. It basically has a very simple consistency model. It assumes that write once, read many. Okay. Worm model. Okay. Essentially, that means once you store the data set, typically files don't change. Okay. If they change, you will basically delete the whole file and create a new version of the file. So you are not designing the file system to make files modifiable. In any traditional file system, you can always read a file, make some changes, and save it back. Okay, HDFS assumes that that will not happen, that you will create files, but once you create files, you will not change it. Okay, which means it essentially uses worm model. Of course, you can change it, but it's only append-only changes, not really, you can't change something in the middle of a file, which is true if you are processing data sets typically. Okay. And we'll see that it actually, when you do HDFS or Hadoop, that you are actually going to optimize how data is read and so on. But here's a picture of how this file system works. Okay. Essentially, there are 2 kinds of nodes you will see here. There are what are called data nodes and metadata nodes. Okay. Metadata machines essentially keep track of where the data is stored. Okay. Data machines actually store the data. Okay. So you will see these green blocks here are actually blocks of a file. Okay. This blue node is a metadata node. This keeps track of file 1 has 10 blocks, and it will say where are the 10 blocks. First block is here, second block is here, third block is somewhere else. So it will essentially keep an index that tells you where the data of a file is stored. Okay. Now this is a common architecture for many large distributed file systems, which is separation of metadata from data. Okay. There are some nodes, machines of the file system that don't store any data at all. All they keep track are index structures as to where the actual data is stored. And there are some nodes where there is no metadata at all. They only keep chunks of blocks, and what those chunks mean, what files they belong to, that information is stored on your metadata nodes. Okay. So there is separation of data and metadata. And you will see many file systems that use the exact same organization of separating the two. That's the first concept. The second concept is you are going to, in HDFS, you are going to use very large block sizes because the files are themselves large. Okay. In normal file system, the block size is about 4 kilobytes. If you have a 100 megabyte file, you will create n 4 kilobyte chunks and then store those 4 kilobyte blocks on your disk. In this case, because files are assumed to be large, your block size could be megabytes or tens of megabytes, not kilobytes. So typical block size would be 64 megabytes. Okay. So you might have very large files which are terabytes in size. You will now partition them into 64 megabyte chunks and store those chunks on your file system. Okay. So that's the second concept. The third concept is that there is replication just to prevent disk failures, because you have multiple machines. Disks can fail, so you are going to replicate data. There is no attempt to using anything like RAID. It's the standard HDFS model is take every block, create 3 copies and store 3 copies on 3 different machines. Okay. So even if 2 machines just crash, you have a third copy somewhere. Okay. So it is basically not even doing mirroring, it's doing factor of 3 replication. Mirroring is factor of 2 replication. Okay. So here, of course, you can change the replication factor. That's a configurable parameter in HDFS, but the default is 3. So every file will be partitioned into blocks. Every block is stored on 3 different machines. Okay. So that's the default model for HDFS. Yeah, so whenever you want to, just the red orange client, you want to read a file, first you go to a metadata node saying I want this file. Okay. The metadata node will look at its index and say this file has n blocks. And then it will say block 1 is stored on these 3 nodes. Go get it from any node you want. Then the client will say, okay, this node is nearest to me in the network. And I will go and fetch it from the nearest node, which might be a node on the same rack or whatever metric you want to use. Then it will say, where is block 2? And it will say, block 2 is stored on these 3 other nodes. So you go to one of those nodes and get a block. If any of those nodes have failed, you will go to an alternate server and get your block. And this is how you are going to keep reading data. Okay, is that clear? Okay. So just want to show you how the Google file system works, which is very similar to HDFS. Okay. So this is a file system that Google came up with. It's called GFS, and it has a similar architecture. You will see that there is a master node which acts like a metadata server. So it has a file system tree, and then for every file it has a table which says where are the blocks stored. Blocks are called chunks in Google file system terminology, and each chunk is again replicated on at least 3 nodes. Okay, so replicated thrice. Okay. And there are chunk servers, okay, which are essentially standard machines which are just running Linux. Okay. And each chunk is actually stored as a file internally on Linux. Okay. You can just name the file as chunk 1, chunk 2, chunk 3. So you can just make files which have these names, and then you're just going to store them on a standard Linux file system. Okay. So and then you will take each chunk, which is a block of a file, replicate it 3 times. So if you, again, this is designed for large files. You will partition their file into chunks, and chunks are much larger than standard disk blocks. Each chunk is replicated thrice, and then you will store it on a chunk server, which is a normal Linux server. And then the read process is the same. Your client is going to say, I need this file, and this block of the file, you are going to essentially go to the metadata server, get the blocks from wherever, whatever is closest to you. Okay. So very similar architecture to whatever is in HDFS, and there are many other file servers that use the same architecture. Is that clear? Any questions about this? So there are, this is just a one slide overview of Google file system. There's an entire paper that describes this. That's part of the reading list. If you're interested, go look at it. Same with HDFS. Okay. So I'm going to stop here as far as file systems are concerned. Switch to the next topic, which is distributed middleware. Okay, so again, this is going to be a high level overview of various different middleware systems. Okay. We will see a lot of them are object oriented systems. They use concepts like RPCs and RMIs, which we have already looked at. Okay. So what this is essentially a case study that says how are some of the concepts that we studied early on in this course, how do they come together in these systems? And we are going to look at 4, okay, maybe 3 today and 1 next time if we run out of time. But so we'll look at DCOM, CORBA, EJBS and Jini, not necessarily in that order, but all 4 of them. So let me start with distributed objects, which is a picture that you should have seen before. When we did RMIs, we essentially had exactly this picture, which said here is a client. Client has essentially a stub, which is called a proxy. Okay, the object that you are trying to access is on a different server. Okay. And essentially, the gray box is the state of the objects. Those other boxes are methods on the object. And if you are making an RMI call, the client code is calling a method on this object that's stored on a different machine. Okay. So the request is sent over a network. It arrives at the other end, and then you execute the request. Okay. This is remote methods. Okay. Now, distributed objects are different from remote objects in that this object is itself now partitioned across multiple machines, not replicated, just partitioned. Okay, you might have, it could also be replicated. Okay, you might have the parts of the object on different machine or replicas of the object on different machines and so on. Okay. So the general concept of a distributed object is a remote object, but its state could be replicated or distributed as well. So it generalizes the concept of remote objects that we already studied earlier. Okay. So essentially, this is just showing you all of the differences. So RPCs, there's no object-oriented concept as we've seen. It's the ability to just call methods on a different process running on a different machine. Okay. RMIs make RPCs more object-oriented, where the methods, procedures you're calling are essentially methods on objects. The objects are stored remotely. Distributed objects have RPCs or RMI concepts, but they also allow you to look up distributed object references. So you can pass pointers around, okay, which are network pointers. Typically in RPCs, you cannot pass any pointers. Okay. In distributed objects, you can pass pointers, and I'll show you an example of how pointers can be dereferenced, even if they are pointing to some object on a different machine. Okay. So one slide, very quick overview of how all of this evolved. So very early on, there was this notion of remote procedure calls. Okay, there were multiple implementations of remote procedure calls that kept evolving, and those have evolved into middleware systems, okay, which are DCOM, CORBA, which we'll look at. And then there was Java RMI. Java had its own RMI method that evolved into a middleware system called EJB or Enterprise Java Beans that we'll also talk about. Okay, so we are going to look at DCOM, CORBA, EJBS, and there's one more that's not in this picture called Jini. Okay. Now, originally when some of these middleware systems were developed, okay, the developers thought that they will be used to design very complex distributed applications like what is shown here, where each of the circle is an object that's stored on different machines, and objects just communicate with one another, and then you have some distributed object, distributed application implementation. Okay. What has really happened is these concepts are actually used in a more client-server style framework, where there's a client and there's a server. The server itself may have distributed some content across multiple machines, but it's basically this kind of model rather than this model. Okay. Which means also that some of the middleware systems, because they were designed for this more general case, are a lot more heavyweight than how they actually get used. Okay. So they're designed for a scenario that was a lot more complex than how developers actually write applications. Okay. As a result, some of those systems essentially became commercial failures. They became products, but they were so heavyweight nobody adopted them and they never went anywhere. So we'll see CORBA as one of those examples. Okay. All right. So here, just to give you a sense of how you can have a pass an object reference, object pointer by reference. Here's an example of a CORBA pointer. Okay. You will see that the CORBA pointer is not just a memory address. Typically, when you talk about a pointer, is essentially a memory address on a machine. Okay. In case of CORBA, the pointer actually has multiple pieces of information in it. You will see there's something called a repository identifier, there's profile, all of that we don't need to worry about. What I would like you to look at are these three things. There's a host information in the pointer, there's a port, socket port, and there is an object key, okay, which is essentially the memory reference part of it. So you will see that in a network pointer, okay, you essentially say if you want to dereference a network pointer, you say this is the machine this object lives on. That's the port number that the object can be accessed on, and here is the object reference itself, which has more information, but think of this essentially as the memory address of that object within a process. Okay. So we have generalized the concept of a memory pointer to, in CORBA, a very complex object entity that's essentially a network pointer. So now you can dereference this network pointer, and you will know which machine does this object live on, how do I communicate which port number, and then where is the object within that process on that port number. Okay. This should just give you some sense of how a simple notion of a memory pointer has become a lot more complex, because you're allowing objects to be passed as references rather than by value. Okay. I'll come back to CORBA in just a moment. Okay, but let me talk first about our first middleware system, which is Enterprise Java Beans, or EJBS. Okay. So this is the standard middleware on Java. If you write any code in Java that is deployed in any large organizations, it will be built on an EJB framework. Okay. So what EJBs are, they take standard Java that you must be familiar with, and they add a number of additional middleware services that allow you to write complicated applications. And so you'll see there are a number of services. There is RMIs, which is a standard Java service. There's JDBC. Okay, this is the service you use to connect to databases and read and write database. They provide you a standard interface to talk to any database. Okay. There is JMS that essentially allows you to, is Java messaging service. It allows you to send messages in an MQS type. Okay. And then there are many other services. Okay. And you write code in EJBs as essentially what are called beans, and I'll show you an example of what these do. Okay, so here are, now as far as EJBs are concerned, conceptually they're still Java code, okay, but they're written on top of a Java middleware that allows you to use a lot of the services out of the box rather than having to write all of the code yourself. That is true for every middleware system we are going to see. Okay, they'll provide us with a number of extra services, so we don't have to write that code ourselves. And I'll show you many other examples that are a lot more complicated than EJBs. Okay. But the main thing that this middleware service provides, in addition to having all of those services, is the notion of an entity bean. Okay. And this is just a fancy name for a persistent object. Okay. So you should try to understand what a persistent object is. Typically, if you write code that is object oriented and you construct an object, that object is stored in memory. Okay. If your process is terminated, that object is gone, okay, because the entire memory state is wiped out. What a persistent object is essentially the object lifetime is independent of the process lifetime. Okay. The application can shut down, but the state of that object is actually stored on disk, and then you can start another process and reconstruct that object by reading it back from disk. Okay. So think of a persistent object as similar to being a file, because files are basically persistent data that you store on disk. Okay. Just because you shut down the application doesn't mean all the files it was accessing are gone. They still live on disk, and you can read them at a later time. The same is true of these objects. Okay. You can essentially shut down your application, but any object that is persistent will be saved on disk, and later on it can be reconstructed in memory. That's the main thing that EJBs will give you that you don't have in standard Java. You can of course do that in Java by serializing the object and manually storing it on disk and then reading it back, but EJBs do that automatically for you. Okay. So there are 4 types of objects you have in EJBs. There are 2 memory based beans, which means they are not necessarily persistent. One is stateless session beans. So this here the object stays alive for the duration of a session, And as the stateless suggests, it has no state in it, only methods. Okay. And there are stateful session beans, which are the closest to what is a normal object in Java, that it has state, which is all its private variables, and it stays alive for the duration of the process until you delete it. Okay. But the main one is the entity beans, which are essentially persisted on disk. Okay. So you can essentially shut down your application, but that object is not terminated. It will be saved on disk for you. And then when you restart the application, you can reconstruct it. Okay. And there are something called message driven beans that are simply used for messaging or sending messages to one another. Okay. So you get all of these extra features that you will not have in a normal Java so when you write Java code. Okay. But if you are writing your Java code using an EJB framework, all of these additional features come for free. You can just use them in your code without having to basically construct entity beans and so on. Any questions here? Okay. So the next middleware, that was a very quick introduction to EJBs, and we are going to build from there and look at a lot more complicated framework or middleware framework called CORBA. Okay. CORBA is essentially an acronym that stands for Common or Object Request Broker Architecture. Okay. At the heart of CORBA is essentially what is called an ORB, or a request broker. Okay. That's shown in this picture here. Request broker is essentially a communication channel that allows objects to communicate with other objects. Okay. So it's an object-oriented framework, and they all communicate with one another through this communication channel that's called a request broker. Okay. Broker is supposed to be an intermediary that enables communication. Okay. So that's a standard term that is used in distributed system. A broker is essentially a middleware entity that enables other objects to communicate. Okay. And that same concept is present in CORBA. Okay. So it's essentially the ORB, or the object request broker, is at the heart of the middleware system. That's what enables various things to communicate with one another. Okay. Now sitting on top of the ORB, you will see a set of services. There are object services, there's something called horizontal services, vertical services. Those all come with the middleware framework. Okay. And your application code is essentially objects that you write yourself. Okay. So they can use other services to implement the application, or you can implement your own services. Okay. So that's the basic idea. And the part that is interesting in CORBA is that the number of services is quite extensive. What the middleware gives you is a very long list. Okay. Here is, I don't know if you can read this, but this is a list of services that come out of the box in Java. In CORBA. So you will see there are things like event service, which I'm going to talk about. There's a transactional service. So if you want to implement transactions, that's already in there for you. Okay. There's a query service that allows you to do querying. There's a persistent service which allows you to make your object persistent, which is the same thing you had in EJBs. There's a security service which will automatically encrypt communication and files. So you don't have to implement encryption yourself. You just call the security service. It will do whatever you needs to be done. There's a notification service, a whole set of them. There's a concurrency service that will automatically make your code multi-threaded and so on and so forth. Okay. So lots of features are included in the middleware. Okay. And so you don't have to write a lot of code to implement sophisticated application. That's a good thing. The bad thing is that there is a lot of overhead. If you're trying to write a simple application, you may not need 90% of what is in there. Yet you have to run it all in order to implement your code. This makes your application very heavyweight because the middleware is very heavyweight. Okay, so it only makes sense to use it when you're trying to write a really complicated or complex piece of code which can be easily implemented because many of the features are built as services already. Okay. If you're trying to do something relatively simple, there's a large learning curve because first you have to understand all of those services to make sure you're using the right one. Okay, in order to write any code at all. So there's learning curve for the developer, but there's also a lot of runtime overhead because of all of this. Okay. So this was one of those middleware systems that were built assuming everybody will start building very complicated applications. They will need a lot of sophisticated features. So let's implement them all as services, and then the developer can just write a little bit of code and use the services to implement the rest of the application. Okay. That's not what happened, okay, because the CORBA ended up not becoming very successful commercially. Okay. because it was too complicated. It slowed down your application so much that people basically did not, or rather developers decided it was not worth the trouble writing things in CORBA. There are many other middleware frameworks that met the same fate. Another one called DCE, which stood for Distributed Computing Environment. It was also an object-based middleware system, also had the same problem. Okay? Too heavyweight, didn't really work because it was too much of a learning curve and had too much slowdown. Okay? But in the 80s, 90s, and even in the early 2000s, there are all these different middleware systems that were built. Okay? Now everything is done using web. That seems to be the standard way to implement large distributed applications, not use this kind of middleware. Is that clear? Okay, so good to learn what these middleware systems did, but they of course had their shortcomings. Okay, but I do want to talk a little bit more about CORBA before we move on. Okay, so here's a picture of how RMIs work in CORBA, and you will see very similar things as a standard RMI based interface. The client orb acts as a stub. Okay, and there's a server orb, which is a server stub, and then essentially you have an ideal proxy that allows you to write your part of the stub. The application code is written at the top. Everything below the application code is either a Corba service or is auto-generated code. So you don't have to write that. You're only writing the client part of the application that's at the top and the object implementation on the server. Everything else comes for free, but you will see there are lots of different components. Okay, so there is a object adapter that gives you something called portability. You can write some code in one language and other code in another language. Okay? CORBA is designed to be language independent. Okay? Not only is it OS independent, you can write the clients and the server in different programming languages, and it still works. Okay? Because they wanted this to run with complicated application, they said let developers use their own choice of language and it will still all work with one another. So if you have that, then you need portable adapters that make all the calls work across different language runtimes and whatnot. Okay, so a lot of sophisticated features of this sort that are essentially part of CORBA. Okay, but there is, and then here are some ways you can make RMI calls, and this will be familiar to you. Way back when we were talking about RPCs and different RPC modes, we had synchronous, asynchronous, one-way, deferred synchronous. All of them actually come from CORBA, because you will see the synchronous RPC calls. There's a standard RPC call. There's one-way RPC where you just send a request, don't even wait for an ACK. There's deferred synchronous where you make two one-way RPCs. You send a request and the response comes back also as RPCs. Okay, we had looked at this when we were talking about RPC models. Okay, so they all come from CORBA because CORBA actually implemented them and said you can use whichever RPC method you want. Not only that, you also have failure semantics that are associated with this. So synchronous is at most once, one way is best effort, and deferred synchronous is also at most one semantics. Okay, so they'll have different failure semantics that are spelled out for you as well. Okay, so you'll see now how some of what we had studied more in the abstract earlier in this class are actually implemented in systems like CORBA. Okay. So I won't spend too much time on the RMIs and RPC part of CORBA, but I do want to spend a little time talking about a different service in CORBA that's interesting, which is called the event and notification service. Okay. So this service can be used to deploy publish subscribe applications or pub sub applications. Okay. So as I had mentioned earlier, this pub sub model is one way to implement a distributed application where your application has publishers that create data or events, and there are consumers that consume data or events. Okay? And then in CORBA, the event channel is the intermediary that connects publishers to subscribers. Okay? So which is why it's called a publish subscribe model. Okay? So here is a picture that shows you how this works. So you have part of the code written as suppliers that are simply generating data or requests. Okay? All of those data requests go into the event channel. Basically think of this as a queue, and then your consumers are subscribed to certain kinds of events. That's why it's called a pub sub model. And you can say if any event that matches this characteristics arrives, or any data that matches this character arrives, push it to me. So the event channel will have a list of subscriptions, and every time an event is published, it will look if there's any subscribers that have, or consumers that have subscribed to it, and then push that event. Okay? So this is a push-push model where data is pushed from the publishers to the event channel pushes data to the consumers. Okay. The event channel is the part that Corba already implements for you. Okay. So if you want to write a publish subscribe application, you simply use the event service, and then you use the interface of the event service to create new events, and consumer part of the code that you write can actually subscribe to events, and then everything just works. Okay. So this is a push model. You can also use a pull based model, which is also using the same concept. Here the event channel is polling the subscribers saying, do you want to publish any new data? So you are pulling new data from the suppliers into the event channel, and they are queued there. And the consumers have to also poll the event channel to see if there is any data that they have subscribed to that has arrived, and they will take delivery of that. So you can pull data from the publishers into the event channel, and consumers can pull data from the event channel to the consumers. Okay. So that's one approach. So in this case, as you can imagine, as we have done client pull many times, you will have to periodically poll to see if any new data has arrived. Okay. That might be wasteful if you do not know how frequently data is being published. If you start polling every second and data gets published every few minutes or hours, you are going to have lots of wasted messages. Okay, so what is something you can do to avoid this? Dynamic pull. Okay, that's one approach. What else can you do to reduce the overhead of polling? What concept have we studied that we can actually use so that the consumers don't have to poll needlessly? No. Okay, you can use events. What does that mean? Okay. So you are almost right, which is essentially using asynchronous method invocation. Basically, you ask for a callback. Rather than polling, you say, tell me if new data has arrived and notify me, then I will pull. Okay, so you will essentially get a signal saying data has arrived. So then only then you pull. So you just wait for to be told new data has been published. Okay, that's a good question. I was going to ask that question, saying what's the difference between push and asynchronous notification? In a push, data is actually pushed to you. In an asynchronous notification model, you are only told that new data has been published. You still have to fetch it from the event channel. Okay, so there's a small difference between the two. Okay, yes, question.
How does it differ in terms of performance if you use push or event pull? How does it differ?
So question is, how does the performance of push versus asynchronous? So there are three models: push only, pull with asynchronous notification. Okay, so in a push-based model, every time there's an event that's going to be pushed to you, which is what was shown here. Okay. It's going to push to you. So there's one message per event going between the event channel and the consumers. Okay. In a pull model, pure pull model, essentially you are going to keep polling, and whenever data is published, you are going to get it. Okay. So there may be a lot of wasted messages if there's no data published. But if there's frequent data, there's no problem, because you will essentially keep pulling and new data may have gotten published. I mean, in an asynchronous plus pull model, there will be two messages. Every time data is published, you will get a notification, and then you go and pull. Okay, so it is much better than a pure polling model, poll model. But in terms of overall message overhead, the push-based has the least message overhead. Okay? And then the next best will be an asynchronous pull in terms of pure message overhead, not necessarily runtime execution cost or anything. And the pure pull will have the least efficient, because that will depend on how frequently data is published versus how frequently you are polling. The relative trade-off will depend on those two metrics. Okay, is that clear? Okay. So here is essentially the same thing that I mentioned. You can make a request. Okay, you'll get a response. Essentially, you'll get a response from the server that's registered with the callback, and at a later point, the orb or the event channel will tell you new data has been published. You can use the same thing for RMIs as well. As asynchronous RMIs can also use the same framework. Okay. All right. So I already talked about the polling model for asynchronous method invocation, which is what I was just talking about. So there will be a polling interface here as well that is going to do the polling as opposed to asynchronous notifications. Okay. So next I want to talk about Microsoft's middleware system, because there's a lot of middleware systems that are built on top of Windows, which are separate from everything I've talked about. Okay. In fact, there is a whole slew of middleware systems that Microsoft has actually developed over the years that are now all evolved into .NET. Okay. The modern one that Microsoft has is basically their .NET framework. Okay. But there are many systems that preceded .NET that actually evolved into what is now called .NET. Okay. So we'll talk about COM, which was the very early one. Then we'll talk about Ole, which was another system, then ActiveX, and then what is now called .NET. I'll talk about this picture in just a moment. So essentially, this is Microsoft object model or Microsoft middleware for building applications, which obviously are Windows-based applications. Okay. So in the very first one, which is called COM, was a simple RMI-based framework. Okay. This allowed you to make object requests and on a same single machine, okay, not even across machines. You could have different machines running, different processes, running on the same machine. They could communicate with one another using the COM model. Okay, so that's basically was their first attempt to build a RPC system that was local to a machine, not doing anything distributed. Okay. And then they said the main purpose of you developing COM was to allow Microsoft applications to communicate with one another. And the most common Microsoft applications are Office applications. Okay, so you have PowerPoint and Word and Excel and so on. Okay. So you may ask, why should PowerPoint talk to Word, or why should Word talk to Excel? Okay, so the reason they wanted to do this was they allowed you to embed one type of document into another. Okay, so for example, you could take an Excel spreadsheet and you could embed it into a PowerPoint application. Okay, or you could take an Excel chart and put it into a PowerPoint application, okay, and make a figure. Okay, so now and then you can just then go and click on that figure and edit that spreadsheet, and then the figure bars will change based on what data you enter. Okay, if you used these features in PowerPoint or any other thing, you will know what I'm talking about. Okay, so they saw that there was a need to take one type of Microsoft document and embed it into another type of Microsoft document. And that required that these applications communicate with one another. Okay, if you're embedding my Excel's bar chart into a PowerPoint application, PowerPoint has to actually communicate with Excel to understand how to take the data and show it in a bar graph form, okay, or any other chart form. So this required that you have the ability to embed one document into another, or link one document into another, edit them and so on, which means that these applications had to communicate. And they communicated using an RPC framework, which was COM. Okay. This feature was called Ole, which was object linking and embedding, okay, which is still there today, but it was developed many years ago when they allowed this capability. Okay. Is that clear? Okay, so this was the RPC layer. This allowed Office applications to communicate with one another using RPC layer, allow you to embed one document into another. And then when the web became popular, they essentially took all of this and added an additional layer that allowed you to expose some of these features as web applications. Okay, so you could write what were called ActiveX controls in documents and then have web-based views of those documents and so on. Okay, so this added a web-based layer, which initially only worked, or even today, only worked on Internet Explorer. If you use other browsers, some of these features are not present because this was all built around a Windows platform. Okay, but there are lots of applications built in the old days that used this ActiveX framework, which were a web application, and then only worked in Internet Explorer, not on any other browsers. Okay. So, and then they allowed you to do web-based scripting and so on and so forth. Okay. Now, all of these three essentially then evolved into what is called the DCOM. Okay. DCOM essentially allows you to do all of these across machines. Okay. So you can do RPCs across machines. You can essentially do all of these other things, Ole and ActiveX across machines using a client-server framework. Okay. So they took all of this and said, now, why not have another machine that can actually invoke RPC calls on objects stored on this machine, etc. Okay, so DCOM is essentially what is the equivalent of what you have in Java, RMI, or any of these other frameworks, okay, CORBA and EJBS and so on. And so there are a lot of DCOM based applications that were built, and eventually that became .NET. Okay, so .NET essentially has a language independent runtime. So you can write applications in different languages that are object oriented, and they can still communicate using the .NET framework. The client and the server don't have to be written in the same language. Okay, so they can be you can write them in C or .NET or any other language that's supported by your .NET runtime. Okay, so it builds language independence in addition to allowing you to write distributed applications. So here is an example figure that shows you how DCOM works, and you'll see it's very similar to a lot of our RPC, RMI concepts. So your client application, server application is implemented as objects. Okay, you have your proxy, which is your stub. Okay, there's a DCOM or a COM layer here, which allows communication. So this is auto-generated code. This is the middleware code that already exists. Here also you have middleware code, and then this is auto-generated code. This is essentially your objects. Okay. And like in CORBA and Enterprise Java Beans, objects can be persisted on disks. Okay. By default, objects are not going to be persistent. They live in memory. You shut down the object, shut down the application or the process, the object is gone. Okay. But you can actually save the objects on disk as well, and that is what some of this disk and this SCM layer does. So you have this notion of persistent objects even in DCOM, just as you had in CORBA. Okay. And persistent objects are essentially called monikers in Microsoft terminology. There are many kinds of persistent object, but the main one we are interested in is the class object. Okay. So if you have a class that is persistent, you instantiate that class. You get an object. By default, if it's a moniker object, it will be stored on disk. Okay, you can restart the application, read it back from the disk, and that object will be reconstructed exactly the way it was before you shut down the application. So the objects can live across application start and shut down cycles. Okay, so this is essentially what Microsoft calls persistent objects. Okay, so any questions on this? All right, so there are different monikers which I'm going to ignore and spend the remaining 20 or so minutes talking about a very different kind of middleware system, one that we have not yet seen, okay, which is called a distributed coordination system. Okay, this is also called Blackboard architecture. It's a different way of building essentially distributed application. So let me give you a little bit of examples of what this does. Okay, so if you think about distributed applications, okay, we will see that there are ways to classify them based on what is happening in time dimension and in space dimension. Okay, so your applications can be coupled in space and time, or they can be decoupled in space and time, and depending on what combination you have, you will get different kinds of applications. So the simplest one is direct messaging, where both parties have to be present. Okay, which means they're coupled in time, and they also need to know where the other party is. So you need to know how to communicate. You need to know the host IP address and port numbers and so on. Okay, this is essentially called coupled in space and time. Okay. Then you have mailbox architecture, which is like email, where you are uncoupled in time but coupled in space. Okay, what this means is if I send an email to someone, I need to have an address which is addressing that message to somebody. Okay. That means it's coupled. I know who the receiver is, but when I send the message, the receiver doesn't have to be present actively reading the message, which means it's decoupled in time. The message is read at a later time from the time it's sent. Okay? So that's decoupled here in mail in time, but coupled in space. Okay? There is a meeting-oriented architecture, which is exact opposite. It's coupled in time, but decoupled in space. Okay? So what that means is you call a meeting saying, let's get together in this room at 2:30, okay, which is, let's say the class is going to take place at 2:30. So everyone knows where the meeting is going to take place, okay, because the where it's going to take place is specified, but who is going to show up at that meeting may not be known a priori. Okay, so which is why decoupled in space, okay, but coupled in time. You know when the meeting is going to take place, but not who is going to come to the meeting. So that's meeting oriented. And the last one, which is what we are going to focus on, is decoupled in space and decoupled in time, which means you can communicate. Application components can communicate with one another, but they don't know when they send a request who might read that request and when that request might be read. So it's completely decoupled and is the loosest form of communication, or it's called distributed coordination architecture. So this is the one we are going to talk about, and I'm going to give specific examples of why this even makes sense. So why would you want to send a message if you don't know who the message is for or whether it will be read at all? Does that even make sense? So let's talk about a specific system called Jini, which is a Java-based middleware that was designed essentially as a distributed coordination model. So these kinds of applications make sense when you want to enable things like service discovery. So I'm going to give you an example. Let's say you go with your laptop or your phone and you connect to a new Wi-Fi network. So let's say it's a Wi-Fi network that is in your friend's house. And now let's say you want to print a document from your machine to your friend's printer. So you just showed up at a new Wi-Fi network, you want to print. What would be the normal set of steps you would perform in order to print to a new printer? Sorry, can you?
Add the printer.
So you'll add the print. First you have to configure that printer. You will have to know if it's a network printer, what's the IP address of the printer, what is the model of the printer. You would have to figure all of this out. You will have to enter all of that configuration on your machine. Hopefully you may have the driver, or you have to get a driver, and only then you can print. And all of these tasks have to be done manually by the user. Now what if your machine was smart enough to figure out when you arrive in a network saying, here are all the services that are available to me. There are 4 printers that I can see. There are 2 mesh servers, file servers that I can see. Here are all these other services I can see. And if the user simply said, okay, let's print to this printer and pointed to one of the printers that have been automatically discovered, then the user has to do less work. So in this case, your system can go and discover services that are available in your network, and users simply decide which service they care about and use that service. There is no configuration, manual configuration involved. Does that make sense what I just said? So these are also called zero configuration or zero conf services. In Apple, there's a protocol called Bonjour, which is one of these protocols that automatically goes and discovers what services are available. In every network, if there are other machines that are advertising services, it goes, discovers this, it shows you on a list. Windows also has this auto discovery process where it will show you various services. And the most common thing you see is basically the list of Wi-Fi networks that are automatically discovered for you. That's the most common use of these things today. Most of the time printers can be discovered, but Wi-Fi network, if you click on your Wi-Fi icon, it will show you all the networks shown. You just click on the one that you want. Maybe you have to supply a password for security reasons, but the rest of it is taken care of for you. So these auto discovery things are useful from a user's perspective. Now you might ask, what has this got to do with distributed coordination? So the way these services work is they use what is called a blackboard architecture. Or a bulletin board architecture, where every service that wants to discover itself advertises on that bulletin board. And then other services go and look for what they want on that bulletin board. It is very similar to if you want to, let's say, if you are moving apartments, you want to sell your furniture. What would you do? You make an advertisement, you go and you put it on a bulletin board, and then maybe you write your phone number. This note is not specifically addressed to anyone. Neither do you know if anyone is actually going to be interested in your note. You just advertise and hope that somebody is going to come at a later time, look at your note and contact you. So that's very similar to what's in the bulletin board architecture. You post a message that's not advertised to anyone in particular. And so you just hope that somebody who's interested in such a service will come look for you. So all printers might go and advertise themselves by posting a note on this bulletin board saying, I am an HP printer, this is my IP address, and this is the model number. And then maybe other services also go and advertise themselves. When machines come into the environment, they can go to the bulletin board and look for services they want, and then basically access them because all of the information is in the node. Okay. So now you are posting messages. Unlike a normal message which is addressed to a process or an IP address, you have sent messages that are not addressed to anyone in particular. Later on, other machines might come and look for services and may or may not even find them depending on what's in the environment. Okay. So communication is now very loosely coupled. You are sending messages without having a recipient, or whether you don't even know whether the message will actually reach a recipient, because no such recipient may ever come looking for a printer. Okay. Yet you go and advertise. Okay. So this is a very different way of writing distributed application. Okay. This is just one example of where these things make sense, but you can now write any application using this framework where you have different processes that simply go post a note on this bulletin board architecture, and other machines can go and look for notes that match certain attributes at a later time. Okay. So in the case of Jini, this bulletin board is called a Java space or a tuple space. Okay. It's like very similar to a shared data space that's going to store tuples. Each tuple is a message, okay, and essentially it points to a Java object. And then you can go and query the tuple space to find matching objects or matching services, or you can post new objects. Okay. So here is a picture of how this works. So this approach also uses pub-sub style architectures. Okay. So publishers are going to go and post notes on your bulletin board. Subscribers are going to go and query saying, tell me all notices for printers that have been posted. And then every note that matches type printer will be returned to you. Or you can ask for some other service, saying what Wi-Fi networks exist or what access point exists in this Wi-Fi network. All of that is going to get sent to you through a bulletin board architecture. Okay, so here is an example of how you can do reads or writes. So here is your shared Java space. Okay, this is your shared tuple space. This is actually distributed on multiple machines. It's a distributed application, but here is shown as a logically single bulletin board. Okay. So you will see that this application has posted a note A. That application has posted a note B. Here's an application that comes and says, I'm going to query the tuple space, send me all messages that match a certain attribute. Okay. In this case, that attribute matches C. So you can essentially return C and also remove it, saying I can take the note off, or I can just read the note but leave it there. Okay. So this is how you are going to implement your application. The Java space is going to be implemented by Jini. Okay. What you read and write is dependent on each application. What object or nodes you post and what nodes you take off is essentially going to be dictated by what application you are trying to write. Okay. So here's an example where you will get a notification. So you can use the publish subscribe model where you can say, I'm not going to keep polling. Anytime there is a new message or new node that matches type T, notify me. And then you register yourself with the Java space. And when some application comes and writes C, you will get a notification saying there's new message that matches something you subscribe to. Then you essentially go step 4, you'll go and say read that message and you'll get it. Okay. Very similar to the asynchronous notification in Corba's pub-sub model. Okay. The same kind of architecture is present in Java spaces as well. Okay. So you can do pull-based or you can do notification-based discovery. Okay. And here are some examples that show you how the Java spaces are distributed across machines. Okay. So you will see essentially that you can have full replication or your distributed Java spaces. Okay. In full replication, what happens is, so if you have full replication, what happens is the bulletin board is replicated in multiple locations. Okay. So think about that's a bulletin board on the first floor, second floor, third floor. So if it's replicated, that means you go and post the same note in every location. Okay. So if you are selling a furniture, you put 3 notices in 3 locations. Then when somebody is trying to read, they go to the local bulletin board and they just look for matching notices. Okay. So writes have to be broadcast to all replicas, but reads are local because every note is posted at every replica. Okay. That's one model. Okay. The other model is distributed bulletin board, where each bulletin board only has a subset of the notes. So when you're writing, you go and write or post a note to your local bulletin board. But when somebody is reading, they have to go and look at all of them. Say if you want to see if someone is selling furniture, you have to go to the first floor bulletin board, second floor, third floor, and look for all of them, because some notes may be only on the first floor and not on the second floor. Okay? So in this case, writes are local, but reads have to go to all the bulletin boards, and you have to get all the matching attributes. So you can have both of those scenarios where in one case the bulletin board is replicated, in the other case it's distributed, not replicated, but you have to basically then go and read all of the entities to get whatever you are trying to get. Okay, so this is the second model where the write is done locally, but then the read you will see is actually going to all the entities. And in the first case, you will see the write actually went to all three, and then the read is only going to a local one. Okay, so you can configure in Jini either of these two models where you are either going to replicate your writes, or writes are local but reads have to actually go to all the replicas, all the bulletin board entities. Okay. So this is essentially another middleware system. Of course, it hasn't actually taken off, but there are other distributed coordination models that were that became more popular. Jini was specifically designed for embedded devices or sensors. So what the Jini developers thought is, in the future there will be lots of sensors, and we will have Jini running on each sensor, so other entities in the environment can go discover the sensors or embedded devices and then talk to it. Okay, the example that they like to give always was this notion of an intelligent toaster, where your toaster was connected to a network, and then you could go and discover that there's a new toaster and communicate with it and so on. Of course, there are no intelligent toasters even now, but you do have intelligent refrigerators, although they don't use Jini or anything like this. But the point they wanted to make was there will be lots of devices. Manual configuration of hundreds or thousands of devices is going to be hard. So you need a way to automatically see what is in your environment, find the right kind of device, and communicate with it. Okay. That idea is still valid today. Okay. Although Jini is not the way it actually evolved, but that is the vision they had when they developed this middleware. This is why they chose a loosely coupled model where you did not have to do manual configuration. You could essentially have devices advertise themselves, other applications go and discover what is available and use those services. Okay. The other place where this kind of architecture is used is essentially, as I said, zero configuration services, where you take your machine into a new environment, it will show all the services that are running, discover them, so you can use it, so humans don't have to actually do any manual configuration. Okay, so that's another place where not that Jini is used, but this distributed coordination model is used for various different kinds of applications. Okay. So we have a couple minutes. I'll see if there are any questions before wrapping up. All right. Any questions about the lab? It's due in less than 6 hours. Okay. So let's stop here. Next time I'm going to talk about data processing systems, and then we'll talk about security. Okay.